Hello, dear viewers, and welcome back to yet another episode of Binagraphy. I'm your host, Mac May. Today, we continue our infinite part series on infinity. Today's topic, from here to eternity, proof by induction. Everyone knows infinity is big, but do you know how many infinity there are? Consider numbers. Take an infinite set of them. Remove an infinite set from that set. You still retain an infinite set of numbers. The set of real numbers is infinite. It contains the set of rational numbers, which is also infinite, and which contains the infinite set of integers, which itself contains the infinite set of natural numbers. Between any two numbers is another bound yet infinite set of numbers, 0.1, 0.01, 0.001, and so on. An infinite array of infinite sets, all within 4 infinite sets. Obviously, infinity is something mathematics has to deal with. But how can one prove something to infinity? Obviously, you can't just prove every case. Our show is only 5 minutes long, and that would take until well past the end of time. Instead, we use something known as a proof by induction. It is said that art holds a mirror up to life, while a proof by induction holds a mirror up to, well, a mirror. Basically, it's a small, man-made infinity, like you'd get if you held 2 mirrors facing each other, which we can use to prove something to infinity. Consider the following hypothesis. The sum of k cubed for k equals 1 to n equals n squared times the quantity n plus 1 squared all over 4. Without limits on n, this equation goes to infinity. So how do we prove it? Well, we prove the next case. In perpetuity, we prove that if any case is true, that means the next one must be. Like a slinky going down an infinite stair, if we can prove that each step must lead to the next, we don't need to prove each step. We just mathematically know it to be true. So, how do we prove by induction? Well, n can represent any given number. N could be 3, so the next case would be 4. N could be 5,427, so the next case would be 5,428. The point is, whatever n is, the next case will always be n plus 1. Well then, what do we suppose that it equals? Well, it would be the initial equation plus one more iteration. Since the root of our equation is k cubed, if we're trying it with n plus 1, that means we will add n plus 1 quantity cubed. As part of our proof, we are assuming the initial equation, checking to see if it's true. Thus, we are allowed to substitute this part for the other half of the equation. My, that is quite the equation. But what does it all mean? What are we trying to equate it to? Well, if all this is true, then the sum of n plus 1 should be our initial assumption, changed so that every n is n plus 1 instead. And thus, we get this. Now, can we prove that the two sides of this equation are equal? First, let's multiply this part by 4 over 4, which we can do because that's just multiplying by 1. Now that we have a common denominator, this half is all just over 4. Since both sides are over 4, let's multiply both sides by 4 to clear that up. Now on this side, we can factor out an n plus 1 quantity squared, leaving just an n squared plus 4 times the quantity n plus 1. Distributing 4 gives us what looks very much like a polynomial expression. As it happens, both factors are n plus 2, which we can write as n plus 2 quantity squared. For our final step, let's go over to this side and add 1 to 1. And just like that, our equation balances. The hypothesis proven, and we know that any case proves the next case. But of course, Astute viewers will note that we are not done yet. We've proven that each case proves the next case, but we've never proved the first case. In our analogy, we have yet to see if the slinky can take that first step. We don't have to prove all of infinity, but we do need to get the ball rolling. So let's start with the easiest one. The sum of k cubed from k equals 1 to 1 is simply 1 cubed, or 1. Now for the other half. If n is 1, we've got 1 squared times 1 plus 1, which is 2, squared, which is 4, which is 4. Divided by 4, that gives us 1. And that simply, we have our base case. The slinky has started its infinite trek. The first domino has fallen. Alea iacta est. Thank you, dear viewers, for taking this infinite journey with me today. I shall see you tomorrow for our next